Okay, now to continue AP Stats, we talked about our OR, our disjoint and mutually exclusive, and how to use the addition rule to solve. Now we're going to move on to conditional probability and just do a couple problems here. First of all, conditional probability is denoted like this, and it means the probability of B given that A has already occurred. Conditional probability. The formula for that is you're going to find their intersection, the probability of A and B, and divide it by the probability of A. You always divide it by the condition, the probability of the condition. Notice that. So you would use this whenever you're trying to find, when you see words like given that or knowing that something has occurred, the probability of another thing occurring. So on this problem, what is the probability with our same group of freshmen, sophomores, juniors, seniors? What is the probability the randomly selected student is a girl given that she is, the student that we're picking from is a sophomore? Probability that we're going to pull a girl given that we know it's a sophomore. Okay, so we're going to use the formula, probability of being a girl and a sophomore, divided by the condition here, the probability of being a sophomore. Probability of being a girl and a sophomore, we have already talked about, is 8 over 60. 8 sophomore girls over 60, the grand total. The probability of being a sophomore is 15 over 60, 15, the total sophomores over the grand total of 60, which simplifies to 8 over 15. Now this conditional probability should have been really obvious without even using our formula here, but like I said earlier, I want to make sure you can use the formula and do it with the chart, but notice that a conditional probability is almost, I don't know, like a fraction. The probability of girls given that it's a sophomore, there are the numbers, 8 out of 15. And we've done those kind of conditional probabilities already. We just haven't really used haven't denoted it that way. So are the events girl and sophomore independent? Now we haven't really talked yet about what's the difference between dependent and independent. Dependent events, you're going to write this down. Dependent versus independent. Events are dependent when knowing one event has happened affects the probability of another event happening. It's totally different than mutually exclusive and disjoint. It has to do with probability. You know that one has happened, so does it affect the probability that the second thing's going to happen? Independent events, if one has happened, that's not going to affect the other one happening. Okay, so independent events, the check for independence will be if the probability of A is going to just equal to the probability of A given that B has already happened. It doesn't matter that B has already happened. Probability A is the same as it would have been before. So we're going to find those two probabilities. If they're equal, then the things are independent. If they're not equal, they're dependent. So this next question says, are these same two probabilities, being a girl and a sophomore, independent of each other? So we already found these. The probability we're trying to check of being a girl, given that you're a sophomore, is that equal to just the probability of being a girl? We just found the probability of girl, given that it is a sophomore, above was 8 over 15. So what's the probability of being a girl? Well, in this situation, probability of being a girl was girl, 32 over 60. And we're here, this is a question mark. 32 over 60 is equal to 3 over 15. So these events are independent. So what does that actually mean intuitively? Well, it means Yes, the probability of picking a girl doesn't change if we knew ahead of time we had a sophomore. Just because we picked a sophomore, it was the same probability of getting a girl if we knew it was a sophomore than getting a girl out of the total. 8 over 15 either way. This second example are the events girl and junior independent. Probability of girl given that it was a junior, and we could do this the other way. We could have done junior given that it was a girl. And we're trying to see, is that equal to the probability of pulling a girl? So the probability of girl given that it's a junior is 7 over 12. Make sure you look and see where that came from. The probability of a girl is 8 over 15. We already found that. These are not equal, so these are dependent events. So in other words, it mattered if we knew that we had chosen a junior, the probability of it being a girl was different had we not known. Okay, and one more page here. Remember we did our addition rule, and that was for our OR problems. For OR problems, we're going to use our addition rule. Our AND problems, we're going to use our multiplication rule. Know those things. So here's our multiplication rule, and if you look back, let's flip back here. Here is our conditional probability, and if we rearrange that a little bit, multiply the probability A to the other side, we will end up with this. So this is the same exact formula that we were just using for conditional probability, just moved around. If we want the probability of A and B, we're going to multiply the probability A times the conditional of B given A. Notice probability A, then probability of B given A. So 2 students were selected at random from school without replacement. What's the probability that the first one is a boy and the second one is a boy, using that little notation? When I do this in a free response, I probably should define that B sub 1 means the first one's boy, and B sub 2 means that the second one is a boy. So this would be equal to, we'd use the multiplication rule, the probability of the first one being a boy times the probability of the second one being a boy, knowing already that the first one's a boy. So what's the probability that the first one's boy? Well, if we look here, there's 28 boys out of 60 total. So this would, of course, be 28 over 60. Now, we have already pulled one boy out. So knowing that we have pulled one boy out, given that that has happened, what's the probability that we're going to get a second boy? So now there's only 59 people remaining. One boy's pulled out, so there's only 27 boys remaining. So if we total that up, we get 756 over 3,540, which is 63 over 295, or as a decimal, 0.21, which makes a little more sense. The probability that they are both boys. So that would turn into an AND problem. Okay, then our last problem here, if events are independent, our multiplication rule is going to change a little bit. Remember, independent means that the probability of B, in this case, doesn't matter that A has occurred. They're equal. Probability of B given A equals the probability of B. So before our multiplication had probability of B given A multiplied by the probability of A. Well, we're just going to replace probability of B given A with the probability of B because they're equal, because these events are independent. Now, this is only going to be able to be used if we know the events are independent. Sometimes we don't, but here's an example where we do. 2 die are rolled. What's the probability that one is odd and the other one's greater than 4? Whatever you roll on one die is not going to affect the probability on the other die. It's just not going to happen. So if we want to do this, we want the probability of odd and greater than 4. So since they're independent, we can just multiply probability of odd times the probability greater than 4. So what's the probability of getting an odd on a die? Of course, it's 1/2. What's the probability of a second die getting something greater than 4? So that means you'll get a 5 or you'll get a 6. So that's 2 out of 6 possibilities, 2 6 or 1/3. And so we multiply those up. And of course, we get 1/6 is the probability of getting odd and greater than 4. Great job.